The percent composition of a compound is very helpful to know if you're trying to determine the identity of a compound that you might have been working with in the laboratory. Let's figure out how to find percent composition. So the formula is like finding the percent of your grade in a class. So for your grade, it's your points divided by the total points times 100. And it's the same thing with these elements and compounds in the laboratory. So percent composition is the total mass of the element that's found in the compound divided by the total mass of the compound, and you multiply it by 100 to get percent. So here's an example. So sodium chloride is 50% sodium atoms and 50% chlorine atoms. But sodium atoms are a lot smaller than the chlorine atoms. And so that means that the chlorine atom is going to contribute more to the mass than the sodium will. To find the percent composition of this, you need to first find the total. So I'm going to add these up. 23 plus 35 plus 45, and I'm going to get 58.45. So this is my total. So to find the percent of sodium, I'm going to take just the sodium mass, this is just one atom of it, divided by the total mass times 100, and I'm going to get 39.3% sodium. You can do the same thing with the chlorine, or you can just take 100 minus 39.3 to find what the chlorine is. So again, the chlorine, take the atom's mass divided by the total times 100, and you're going to get 60.7%. And these two percentages should add up to equal 100. Knowing this data can help us if there's an unknown compound in the laboratory, and the percent composition can help us figure out that unknown. All right, let's do another one. Let's find the percent composition of chlorine and calcium chloride. So for calcium chloride, I'm going to add up the masses. So calcium is 40.08 and chlorine is 2 times 35.45. And total, that gives us 111 grams per mole. So that's my total. To find just the chlorine, I want to take all the chlorine. So that 2 times 35, which is about 71. So I get 71 divided by 111 times 100, and my percent of chlorine should be about 64%. So it doesn't ask anything about the calcium, so you don't have to do that, just the chlorine. Let's figure out the empirical formula from the percent composition. Remember, the empirical formula is the lowest ratio formula. Here's a step-by-step what to do. I almost feel like it's easier just to show you, but you could write down the steps. So if you're given the percent composition of each element, you're going to convert the percent to grams. So you just assume that you have 100 grams of it. So 100% of a compound equals 100 grams. So therefore you just take the percent and you scribble it out and put grams. Then you're going to convert grams to moles using the atomic masses that are found on the periodic table. And then you're going to find the ratio of moles, which means you divide each element by the smallest element mole number. Let's do an example. So in this case, I'm starting with grams, and so I don't have to go percent to grams. I do have nickel, and I have 9.11 grams of my nickel, and I want to convert it to moles. So looking on the periodic table, 58.69 grams is in 1 mole. And when I do my math, I get 0.155 moles of my nickel. Let's do the same thing for the fluorine. So I have 5.89 grams, and grams should go diagonal so I can cancel it. Looking on the periodic table, there are 19 grams in 1 mole of the fluorine. Grams will cancel, and I'm going to get 0.315 moles of the fluorine. All right, the next step is to find the lowest number. So my lowest number is this one right here. It's the nickel. So I'm going to divide each by the lowest number. So this one I'm going to get 1, And for the fluorine, I'm going to get 2. So my answer should be a ratio of 1 to 2. So I need to write it this way, NiF2. So this is the formula, and that's my answer. All right, let's do one with the percentages, starting with nitrogen, 25.9%. I just scribble out the percent and put grams. I'm going to look up on the periodic table and find nitrogen. It's 14 grams in 1 mole. Working the math, I get 1.85 moles of my nitrogen. And let's do oxygen. So oxygen is 74.1%. Remember, you scribble out the percent and put grams. And I have 16 grams in 1 mole of oxygen. And doing the math, I get 4.63 moles of my oxygen. You're not done. You need to divide and find the ratio. So I'm going to divide each side by 1.85. And my ratio I get is 1 to 2.5. So that's a little strange. So I have a halvesy. So that means NO2.5. Well, you can't have half an atom. So what we're going to do is we're going to multiply this by 2. That will get rid of that halvesy. So I'm going to get N2O5. That's my answer. So the problems that I will give you, they're either going to be whole numbers, so they'll be whole number ratios, or you'll see these little halvesies. And if you see that, then you multiply by 2. You shouldn't have anything else that's weird. So if you have something that's like a third, you've done something wrong, because I'm only going to give you whole numbers, or where you'll have half, and then you'll have to multiply through by 2 to get rid of the half. Okay, let's look at combustion analysis. This is one of the more advanced topics of AP Chemistry, but it is on the AP Chem curriculum, and so we do need to learn it. So when we look at combustion analysis, this means that we're burning something in oxygen, and then we're looking at the amount of water or CO2 that comes about. So this is a combustion reaction. So we're given how much carbon that there is because of the CO2, and we're given how much hydrogen there is because of the water. And just a reminder, remember you have some sort of hydrocarbon plus oxygen, and you get CO2 and water. So you can see that as far as the hydrocarbon go, all the carbon will go into CO2. This is if it's a complete reaction. And your hydrogen, it will go into the water. Your oxygen is found in both of them, but you're usually given enough information that you can solve the problem. So let's go through step by step. This is just really a complicated conversion problem, and if you write all your units and kind of think through it, then it makes it so it's not so bad. But let's go through this step by step. So number 1, use the grams of CO2 to determine the grams of carbon. I'm going to get rid of these arrows so that I can see the problem a little bit better. So use the CO2 in grams to determine the grams of carbon. So start with how much CO2 they tell us. It's right here. So that's my beginning number. And I am going to convert it to moles. I get the 44 grams because when I look at CO2, it's 12 plus 2 times 16. So that's where I get the 44 grams of my CO2. Okay, so once I get the moles of CO2, I'm going to turn that into moles of carbon and then grams of carbon. So again, moles of CO2 to moles of carbon and then to grams of carbon. Okay, so in 1 mole of CO2, I find that there's 1 mole of carbon, and that's the ratio. It's a 1 to 1. So I just do this conversion factor. Remember, your conversion factors stacked on top of each other, they should equal each other. And I know in a CO2 molecule there's 1 carbon. So 1 mole of CO2 would give me 1 mole of carbon. So my moles cancels, and I'm left with moles of carbon. And now I'm going to turn 1 mole carbon to grams of carbon by just looking on the periodic table, and there's 12 grams of carbon in 1 mole. And I can do all my math, and I get that there is 1.1 gram of carbon in my sample. All right, let's look at water. When we look at water to determine the grams of water to determine the grams of hydrogen, we're going to do something similar to what we just did up above. We're going to find the water that we begin with. So 0.1500 grams of water. Or when I add up my hydrogen and my oxygen, I get 18 grams of water is in 1 mole of water. Grams cancels, I'm left with moles. Now I'm going to change moles of water to moles of hydrogen. In 1 mole of water is 2 moles of hydrogen. So that's a little tricky part of this. I think that's why the AP board likes it, because they like to see you do all these converting factors and setting everything up with all the units. So my moles of water is going to cancel, and I have moles of hydrogen. And now for every 1 mole of hydrogen, I know I have 1 gram of hydrogen. And multiplying this all out, I get 0.168 grams of hydrogen. We're not quite done with this. I'm going to go on the next slide because it says, what is the empirical formula of this compound? So we're trying to find like how many hydrogens and how many carbons. And in this case, oxygen too. Oxygen's thrown in there. So maybe it's something like an alcohol. All right, so this is our total. And then we have our carbon and we have our hydrogen. So we add up the carbon and the hydrogen and we subtract it from the total, and that's going to give us our oxygen. All right, so once I know the grams of everything, then I just do find the empirical formula. So take your grams that you start with. So this is my carbon, and I'm going to convert it back to moles. And then I have my hydrogen, and it's really the same thing. And then my oxygen, which I just found out. Okay, you're not done yet. You need to find the smallest number and divide through. So my smallest number is this number right here, 0.00833. So divide through each one of these. And this one I get a 1, and the last one I get a 1, and this one right here I get a 2. So that's not my answer though. It is a 1 to 2 to 1, and it's 1 carbon to 2 hydrogens to 1 oxygen. So this is my empirical formula and my answer. So this is kind of a combination of the percent composition and find the empirical formula. Now we're just adding the combustion analysis from it. You get the carbon from the CO2, you can get the hydrogen from the water. And if there is oxygen, they have to give you the total so you can subtract to find the oxygen. And this is how you do a combustion analysis. If you are totally confused, rewind the tape and listen to it over again and see how you line all the conversion factors up so that everything cancels and you get the grams of carbon, hydrogen, oxygen. Then turn it into moles so you can find the mole ratio, and then write your empirical formula. Okay, if you wanted to know the molecular formula from the empirical formula, this is a long step-by-step how to do it. I think it's almost easier just to show you how to do it. But you're basically trying to figure out how many empirical formulas can fit into the molecular formula mass, because they have to give you the molecular formula mass in order to do these problems. So first of all, they give you the empirical formula here, or you would have to find it. They'd have to give you enough information that you'd have to find the empirical formula. They also have to give you the molecular formula mass. So you have to have those 2 bits of information in order to do these problems. So you need to figure out how many of these can fit into that number. And so you do that by finding the mass of the empirical formula. So the chlorine is 35.45, the carbon is 12, the hydrogen is 2 times 1, and all this adds up to equal 48.5 grams per mole. So then you ask yourself, how many 48s can fit into 98? So you put the total on the top and divide it by the empirical formula, and I'm going to get 2. You should get a whole number. So I'm going to multiply this by 2, and I'm going to get Cl2C2H4. So that's my answer. So this is a molecular formula. Again, you have to be given the empirical formula or find the empirical formula, and you have to be given the molecular formula mass, and then figure out how many empirical formulas can fit into that molecular mass. Let's do one example to put it all together. So I have percent composition, and I'm going to find out how many moles they have. Again, I take the percent and change it to grams for all of these, or I find the atomic mass from the periodic table and multiply through. So that's my carbon, and then next is my hydrogen. 1 gram is about 1 mole. And then I have my oxygen, 31.4 grams divided by 16 grams times 1 mole. And I get 1.96 moles of oxygen. Make sure you divide by the lowest number, so don't skip that step. Students always want to skip that step. The lowest one is this bottom number. And multiplying through, I get 2.5. Oh, there's a halvesy. This one is 5, and this one is 1. So I'm actually, instead of having 2.5 to 5 to 1, my ratio is going to be 5 to 10 to 2. So my formula is going to be C5H10O2. This is the empirical formula right here. So now we need to figure out how many of these empirical formulas fits in my 102 grams per mole. And when I add up my carbons, so 5 times 12, and my 10 hydrogens, 10 times 1, and oxygens, 2 times 16, I actually get 102. So this is also the molecular formula. So I'm done. So this is the empirical formula and the molecular formula.